On the sad, lonesome and blue, I was fair as a summer day. Now the summer days are through. You pass through places, and places pass through you, but you carry them with you.
Hello, everybody. Welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. We're going to be talking about solutions today. Now, when I think of solutions, I think of Kool-Aid Man. Kool-Aid's a solution. There he is, busting through a wall. I find Kool-Aid Man very interesting. It's a little strange. Here he is offering you to drink this liquid that's sloshing around inside of him. What exactly is Kool-Aid to Kool-Aid Man? I'm not sure. It's best not to think of it, probably. This guy here, I don't know. I just admired his costume. But anyway, so some definitions. By the way, solutions, I think, is one of the single most important topics in all of chemistry, at least this level of chemistry, and properly understanding solutions is super critical. So I think it's worth taking our time here to try to get some of these key concepts down as good as we can get them. Solvent. Solvent is a substance that dissolves another substance. So in the case of Kool-Aid, your main solvent is water, and very often water is a very common solvent. It's even called the universal solvent sometimes because there's a ton of things that can dissolve. So water is the solvent that we use in many, many cases, although not all cases. So you got Kool-Aid, you got water as the solvent. The solute is the substance that gets dissolved. So in the case of Kool-Aid, the primary solvent by far is sugar, sucrose. That's what gets dissolved, and there's a tiny bit of stuff to make it colorful and flavorful, artificial flavorings and so forth. And then an electrolyte. Now this is a term I've brought up in another video, but electrolyte is a substance that conducts electricity when it's dissolved or in the molten state. And ionic substances always are electrolytes. Substances that use covalent bonding are usually not electrolytes, although they sometimes can be. When we study acids and bases, we'll see acids are a big exception to this. They're covalently bonded, but they are electrolytes. Electrolytes ionize in solution, and in a different video, in the ionic bonding video, I spent a good bit of time talking about this, but I'm just going to kind of briefly review it again. So when we have something like ionic substance, it's in a crystal lattice here, a network of positive and negative charges, positive sodium, negative chloride, so this is a little crystal of salt. When we put it in water, this whole structure breaks apart into separate sodium and chloride ions. Now there are things called weak electrolytes that do this, but only partially, so they may not completely break apart. And I'm sure at some point, if we haven't already, I'm going to show you a demonstration in class of these different levels of electrical conductivity. But so when the process of solvation or ionization, again, I've talked about this before. It's a super key concept to understanding solutions properly. I'm not going to talk about it at length because I have talked about it before, and if you need to review it, I'm going to put a link here to the other video, the portion of the other video where I explain this a little more fully. But again, if it's an ionic substance, if it dissolves, it's going to break into ions, so the crystal lattice separates. I just mentioned sodium chloride in the last slide, calcium chloride. Notice there's three separate pieces here. There's a calcium ion and the two chloride ions. When they dissolve, this whole thing separates out. So we end up getting, for every one of these that dissolves, we get one calcium ion and we get two chloride ions, two separate chloride ions. So it separates into three different pieces. Calcium nitrate, we've got a nitrate here, separates out again into three pieces, this calcium ion and the two separate nitrate ions. That's why they're not chemically bonded anymore. That's why this 2 is out in front. And again, I put that link on there. There's some animations and stuff on there. You could go back and look at on the other video if you need to review and remind yourself of what's going on with this. This is just another picture. It's literally the water molecules. We've talked about polarity. The water molecule is polar. The partially positive end is attracted to the negative ions, so it's literally being pulled apart, and then the partially negative end of the water molecule, which is the oxygen end, is attracted to the the sodium ions. So you kind of get this structure where the water molecules are surrounding the ions. And this is something we'll talk more when we talk about complex ions, probably in year 2. But again, go back, watch this part of the video again, watch the portions of the other video I linked to, and see if you can wrap your brain around this. Or ask me a question in class, obviously. So there's different types of solutions. When we think of a solution, if we think of it at all, we think of probably something like Kool-Aid or salt water, where there's a solid dissolved in a liquid. That's kind of the most common type of solution, and that's kind of what we think about. But that's not the only type of solution, and there's others. Gas in liquid. So, for instance, CO2 can be dissolved in water, and that's the basis of soda pop. Here's the thing. If something is truly dissolved, if it's truly a solution, it's invisible. So, imagine this. Imagine a bottle of 7-Up that you can see before you open it. Before you open it, that CO2 is dissolved in the water, and it's therefore invisible. Then what happens is you open it, you start to see those bubbles. That's when the CO2 is not dissolved anymore. So as soon as it's visible, that's the point when it's not dissolved anymore. Solids can do the same thing. If you've got some salt water and you let some of the water evaporate, or all of the water evaporate, that salt that was invisible will become visible. It'll crystallize, it'll be stuck to the sides of the glass, and so forth. Gas is the same thing. Invisible CO2 in the soda pop, dissolved, open, then the CO2 is not dissolved anymore. It starts to come out. Another thing, I was pretty old before I finally realized what fish are actually breathing, or how they're actually getting their oxygen. What fish do with their gills is they get oxygen that's dissolved in the water. That's where they get their oxygen from. That's what gills do, is take oxygen, dissolved oxygen out of water. They're not, I think I had the misconception that they were somehow getting the oxygen from H2O, but they are definitely not doing that. They are not splitting water molecules somehow. If they were, there'd be a bunch of hydrogen gas coming off of every pond, which is explosive, and it would be a bad situation. So they're not splitting water. They're not getting water from oxygen. They're not getting oxygen from water itself, from H2O. They're using dissolved oxygen that is in the water. You can have a solution of gases, for example, air. Air is a mixture of different gases, by far mostly nitrogen, 78% nitrogen, a little less than 20% oxygen, tad bit of CO2, water vapor, some other stuff. But air is a mixture of gases. It's a solution. You can also have two liquids. For instance, ethanol can be dissolved into water. That's what booze is. Take vodka, for instance. Vodka pretty much is just a solution where 60% of it is water and 40% of it is ethanol. Ethanol is the active ingredient in all alcoholic beverages. That's the stuff that gets people drunk. It is the very same stuff also if you're at the gas station and they add to gasoline. You can run a car off of ethanol. You can also drink it if you're old enough. I'm sure none of you do that, but so it's interesting. People drink it and run a car off of it. I don't think there's too many other substances that can make that claim. So solubility. When we refer to solubility, what we're saying is how much stuff can you dissolve in a given amount of solvent. So there's some things that influence this. Obviously what you're trying to dissolve. Some things, almost none of it will dissolve. Some things, a little bit of it will dissolve. Some things, a ton of it will dissolve. So solubility depends on the thing you're talking about, but it also depends on temperature. If you have higher temperatures, if it's a solid, you're going to be able to dissolve more of that solid, usually. So, this kind of makes sense. Take sugar, for instance. In cooler water, you can dissolve a little bit of sugar. In warmer water, you can dissolve a lot more sugar. With gases, though, strangely, well, it's not strange once you understand how gases work. When we talk in the next unit, it should make sense. But when it comes to gases, it's actually the opposite. The warmer a liquid is, so the warmer water is, actually the less gas that can dissolve in it. And I'll tell you where you may have seen this. So let's say you get a glass of water at night before you go to bed, and you set it on the shelf. It's cool water from the tap. and you wake up in the morning and you notice clung to the side there's a bunch of bubbles. And if you've never noticed this, give it a shot. Do it right now. Get a glass of water, a nice cold glass of water. Let it sit there for a day or two. You'll see bubbles in it. Where did those bubbles come from? Well, they were gases that were dissolved in the water. So when they were dissolved in the water, they were invisible. The water was cool. As the water warms up, in warmer water you can dissolve less gas. So then those gases become undissolved at the warmer temperature, because the warmer it is, the harder it is for them to be dissolved. And then you see those bubbles. So those bubbles come from dissolved gases that were in the tap water before it warmed up. Pressure also has an effect on solubility, not so much with solids but with gases. The higher pressure something is under, the better that gases can dissolve. So go back to that 7-Up for instance. When the 7-Up, before it's opened, it's sealed and it's under high pressure, relatively high pressure, inside the bottle. So those gases, the CO2 dissolves under that high pressure. So it's dissolved and invisible. As you open it, you can hear that hiss. The pressure equalizes. The pressure goes down. The gas doesn't dissolve as well anymore. So that's when it starts bubbling. So that's what keeps the CO2 from bubbling out early, is they keep the can of soda under pressure. Under pressure, CO2 dissolves really well. And then you open it and it doesn't dissolve as well anymore, and that's when it starts fizzing and so forth. So with gases, the higher pressure, the greater the solubility. That's animated twice for some reason. Alright, that's fun. This is just showing you a graph showing you temperature Celsius and solubility. So notice it's milligrams gas per 100 grams of water, and as I explained to you, as you go up in temperature, the solubility, the amount of stuff you can dissolve, goes down. Here's one showing solids, so grams of salt and 100 grams of H2O. I know this thing looks kind of crazy, but it's basically just showing you, in a given amount of water, 100 grams of water, how much of different things can dissolve at different temperatures. And we see that for the most part, as temperature goes up, the amount of stuff that we can dissolve also goes up. There is a couple of exceptions. NaCl actually isn't affected very much at all. But just a little graph to illustrate some of the things I've been talking about. So you would have a solution that's said to be saturated. So suppose you've got a beaker and you start dumping salt in it, stirring it, it dissolves, dump a little more, stir it, dissolves. At some point no more will dissolve. And that's when it's a saturated solution. So maybe you have this pile of undissolved salt. Now, that would be a saturated solution. You've got the maximum dissolve that you possibly can. What would be going on? We're going to talk more about this equilibrium business and the equilibrium unit, but basically what that means is the pile of salt is going to stay about the same size. But that doesn't mean necessarily that nothing's happening, because what's actually happening is a little bit of this salt will dissolve, and at the same rate, some of the salt will become undissolved. So it's like this balance. But we'll talk more about that in the equilibrium unit. I named it twice again, alright. So at any point up until you get that saturated solution, you have an unsaturated solution. So again, you take your beaker, you put just a tad bit of salt in it, dissolved. At that point, you could still dissolve a lot more salt in it, so it is an unsaturated solution. It's going to be an unsaturated solution up until it reaches that maximum. You can actually also have a supersaturated solution. And not everything can do this, but it would actually be something that contains more solute than should theoretically be able to dissolve at a given temperature. So, for instance, like, not all things can make a supersaturated solution. Sugar can, for instance. So take iced tea. Maybe you've had the experience, you get a nice really cold glass of iced tea, maybe it's 5 degrees Celsius. If you try to put some sugar in there, very little sugar dissolves at 5 degrees Celsius. What will happen is most of it will just sink to the bottom. You won't be able to get it to dissolve very well. So what they do, if you've ever had sweet tea, is, whether you're aware of it or not, tea is brewed hot, like coffee, especially in restaurants. Maybe you have like sun tea or something at home. But so, like, I used to work in a restaurant and we had this big teapot, very much like a coffee pot. It just brewed a big batch of tea, and the tea was hot. and when you ice it down. But what you can do is, while the tea is hot, basically boiling hot when it's being made, you can put sugar in it at that point. And then when it's hot, when water is hot, you can dissolve a ton of sugar in it. So when it's hot, you throw the sugar in then, and then as the tea cools down, or maybe you put ice on it or whatever, what happens with sugar is it doesn't become undissolved. Most things would just become undissolved and like recrystallized. The sugar actually doesn't become undissolved. It stays inside the solution. So then you've got this 5-degree, this cold tea that has a bunch of sugar in it, much more than it should be able to have in it. The only way to make a super saturated solution is to heat something up and then cool it down again and have it not recrystallize. So most things won't do it, a few things will. I'm going to show you a couple of what I think are interesting animations here of supersaturated solutions. Supersaturated solutions are often really unstable. So what you're going to see on this next slide is, I'm not sure what it is. It might be sodium acetate or sodium thiosulfate. There's some different things. What the person has done is they've made a supersaturated solution. So they've heated up the water, they've dissolved a bunch of stuff in it, and they've cooled it down, and it didn't recrystallize. And then what they do is they add like one more crystal. And you'll see what happens when they do that. It all kind of recrystallizes because it's kind of an unstable situation. So, okay, here we go. Yeah, it was a supersaturated solution, and probably right before the animation started, they added one more little crystal of, it's probably sodium acetate, and then it all kind of recrystallizes like that. So whoever made this caught it beautifully. I don't think this is in slow motion. This is probably real time. And maybe at some point we'll make a supersaturated solution and do this in the lab. There's another little video here where it's basically the same process, but what the guy does is pours a supersaturated solution onto a table. It probably has a crystal on it, and then it recrystallizes and builds from there. So that's kind of interesting. Anyway, that's all for now for our introduction for solutions. Thanks for tuning in, and we'll see you next time. Yeah, one more time.